Hi there, so now let's move to the next video. This we're here running the simulation. So in this case, I will launch the simulation. By the way, here you can download the Fluent case file. So I'm going to open this one where we have all the case set up, okay? So I will remember you only when you're working here, you need to give the location. So see that I have this file. This is the file I'm going to open just where I have the predefined setup. It's 3D. Let me launch. Okay. So basically we're going to run this case. Okay, pretty much the same case. And I'm just going to show you some additional steps, something that we didn't see in the previous video. We saw how to choose the time step, which probably is the most important thing. So we're here. Let me read the case. We have the case here. Okay. And now that we have the case, okay, we have the mesh, everything. So see that we have all the case set up, we have all the monitors, we have everything ready to run, but I want to show you two things. So before launching, also we need to initialize. See that when you initialize, you have access to these animation controls, and also you have access here to the solution animation. This is important. To set up this one, you need to first initialize. So we already visit the whole case setup. So let's revisit the vertical workflow. So you go here, transient case, choose the turbulence model or any other models you want. Material, choose your material properties. Apply that material to your domain. Okay, so you have different materials. Then set the boundary conditions. In this case, we have all our boundary conditions there. Then reference values to compute coefficients and so on. And now we move to the solution. So in solution, when you are running on a steady, I recommend you to go for the piso. Okay, the computational cost is lower than the couple, but you can do your own benchmarking and see that everything's second order. Here we're using this method, bounded second order controls. We have these methods here. Okay, later we have a video to talk about this on the relaxation. And then reports definition, we set up the mass imbalance, the imbalance between inlet and outlet, the average y plus at the surface of the cylinder. So see that you have it there. Then CD and CL again at the surface of the cylinder. You have it there. Your monitors. Then this is the monitoring the velocity y component in all these points that you created. And here also the x component. Here you have the monitor for the maximum CFL number in your domain. Okay, so like within the previous video, and these are default parameters. Okay, so this is the setup, monitors, nothing to do there. Then we have the cell register, and I want to show you something also that I didn't talk about that in the previous video. So let me show you the velocity vectors. Okay. And let me show, okay, so see that here is a little bit slow because I was showing everything. So I want to show velocity vectors in this plane. Okay, so see that the flow is uniform, but remember that in this case, we have the von Karman street. And actually, all the solutions that you have here, I perturbated the flow just to trigger the onset of this instability, okay? So something similar happens in turbulence. You saw in the first lectures transition to turbulence. Okay, so you can perturbate it, and then you can force the transition out to turbulent regime, or in this case to the full unsteady. If you run this case with this setup that we have here, uniform initialization, it will take longer to unset this one. Okay, so probably I think if what we recall, it will take like in 60 seconds maybe you are going to see that you have the onset. Okay, but there are tricks, okay, that you can use to force the onset of that transition, so you can perturbate the flow and see that you have this faster convergence. Okay, those are perfectly valid. Okay, so in this case I perturbate the flow, and let me show you. Okay, so this setup you can run, you can do your benchmarkings, and you will see that it takes longer to perturbate the flow. And the perturbation that I'm going to add here, I will put it uniform, and then here in the middle I will add a small perturbation, a vector component. So to do that, you need to see here that you have self-register. We already visit this one for adaptive mesh refinement, but also you can create regions. And see that here what I did, created a region, and I gave dimensions of that box. Okay, so I say that this region goes from, you know your dimensions, so you can put something large there, it doesn't matter. Okay, so see that I will put these dimensions and here also. So you are going to create a box. Okay, 0x1. Okay, so here is 1 cell. Okay, see that is creating, selecting a box, all cells within that box, and then in this box here, you can create another initialization, a patch. So let me show you that you have the region here. So first, to do that one, you create your region, you select. So if you are going to work with multi-phase flows, this is something similar to initialize the free surface and everything. But here we're doing that to add a perturbation, okay? So then you go into initialization, and you use a uniform initialization, okay? Normal, but then see this box that you have here, patch. So this box is the one that it will let you select a region of your domain and apply a different condition. So see that so far we have the whole domain uniform with these values. And now let's say that I want to choose region 1, the one that I created, and well, region 0 is the one, it's exactly the same. So this one, the one that I just created, and then you can add here a velocity component. So if I would recall, this corresponds to 5 degrees. So you go here, patch, then x, y velocity, and that's all. If you want, you can perturbate also this one, there is no need, but just x and y. And now if I go here, now again back to vectors, see what happens when I visualize. See that you have uniform and this. And this perturbation will immediately onset the von Karman street. If you put it fully uniform, it will take a longer time. You are going to get the same results, but it will take a longer time. So these are tricks that you use in CFD, and even in experiments. Sometimes you force the flow, you add an instability, a perturbation just to trigger some phenomena. So if for you it's not important to perfectly capture the initial transient and everything, I recommend you to add these perturbations. Okay, there are many ways. So here I just choosing one, you can add sinusoidal functions, that stuff, but this is more than enough here. Okay, so we have this perturbation. I wanted just to show you this one. Okay, so remember, you need to go here, region, self-register, create a region, and then when you initialize, you will have the patch option, and then you can patch the values that you want to put in that region. So we're ready to go. We have everything, all the monitors, and now we initialize calculation activity just to show you something else. So as you click here, remember that also now is a good idea to save your solution every top time step, given time step. So see that here I'm saving every 100 time step, save the solution. Call the solution running, okay, append to this file name the time step, and keep the 5 months recent files. Okay, so this is important, okay, because if you don't save and it may happen that it crashes, you are going to lose everything. So here every 100 iterations, so you can change these values up to you. Okay, then I added this one here, this you need to add it. So let me erase. So by default you're saving this one, this is enough, the Fluent file, but to do animations I like to create here this one, automatic export, and there is a very specific format that I like to use, and there is one video at the end that I want to show you how to use that new tool. So as you go here, solution data export, you have many formats that you can export your data. So I recommend you to use this one, Ensight case, and then here you can choose what you want to export, okay? So see that I want to export pressure, and let's say just pressure and velocity, but you have access to all fields. And no center values, binary, choose the location. As usual, I like to do like this, and I will call it xend. Okay, so now what I'm going to do is that then you need to give a saving frequency. So I want to export the data every 10 time step. and deselect this one. I want to have a single file, okay, with all that information. So see that what is happening here, you are exporting the data in this format that is easier to use to do the post-processing, the animation. So you see all these videos and movies that you see here, I was using another software. I wasn't using the animations in Fluent, okay? It's not because you cannot do it, because there are, here you get something prettier, okay? But just to show you that, okay? This is not compulsory, this is an extra step that I'm showing you, okay? So if you are not interested in doing this animation and this stuff, do not put anything, okay? This will slow down your computation because you are now doing intensive input output, okay? But if you want to keep that data, okay, you need it to do the animations. And if you have large files, also it will take a lot of space. So set up this one, okay? Also double check always that you have here separate file for each timescale. So you are going to save less files. So sometimes you need to do double click to ensure. See that now here it was, I don't know why sometimes it's selected. So deselect. And this is what we want. We just want this basic information, okay? So it's saving all the patches, everything with this information, okay? So you want to save something else. So for instance, we can save here also the mean value. So see that we have access to mean static. So save these values, and you have here the root mean square, okay? These are the fluctuations. You can save that. So we can save this data because we enable unsteady statistic, okay? To see this data here, you need to enable unsteady statistic. So that's all that I wanted to show you here. So now you can run. So I didn't mention, but see here that you have it like this, okay? So if you run here, you are not computing a statistic. If you want to compute a statistic, select here, okay? So now by selecting here, you are computing the statistic every single interval. So it's computing mean values and root mean square, okay? So this is very important when running on a steady simulation, getting this statistic. So sometimes you are not interested in the initial transient. So probably the first 10 seconds you don't compute this, you disable, then stop the simulation and enable, okay? But we got access to also the steady statistic in the here, because we enable that, okay? Otherwise you don't have access. So this, in this case, I will enable this one. I will compute the statistic and see that we have everything set here. So we're using this time step, relatively large, this number of maximum of time steps. So it will run until reaching this maximum iteration. Now I reduce the reporting interval. You remember that we saw in the previous case that it was showing a lot of information. So this is just to reduce the output interval. If you want, you can leave it to 1. So I will leave it to 1. So this will reduce the amount of stuff you see here. And what else I want to do? So also it's something important that you don't have access here, okay? But you can access that in the text using interface, okay? You can set up the maximum flow time. So by default, the maximum flow time is whatever is infinite, no? It's whatever combination you have here. So here you multiply this by this, it will be like 1, 2, 3, it will be 500 seconds, okay? But if you want to run, let's say up to 80 seconds, here you go in the text user interface and you type max flow time, and now you say you want to run. See that in this case I already defined the value to 100. So if you want to run to 80 seconds, you put 80 seconds. So it doesn't matter what combination you put here. You can put a super large value here. It will stop when reaching 80 seconds, okay? So this is a way just to stop in a precise time. So this is all that we have done, okay? So let me save here case. Okay, so I save my case here, and now let me press calculate, and let's wait to see how long it takes. Okay, so I have my time here, okay, and press calculate and see that it's going to set up all monitors, everything. See that we have all the animations, we have everything, okay? So it's setting everything. We're also saving a lot of information to output files. So as you go here, you see that you have all these output files. You have CD, CL, and see that you have this text file where you have all these probes that we put. So you see probe 1, 2, 3, See that you have all the velocity. So then you can do your whole post-processing. So now, residuals. Okay, these are the probes. This is the maximum CFL number. So see that we're going to a CFL something about 5. As I say, this is a selectable 5, still is accurate. Okay. Here you have CL, CD, okay, the Y plus value average. See that we're wall resolving. Then your mass imbalance. Okay, fast maximum of, okay, this is also values of X component. And here you have the plots of the evolution of that. Okay, so in this case, I'm saving that in Fluent proprietary format, this one, HSA, then you can animate it. But also see that you are saving these files here. These files correspond to Ensight. Okay, so Ensight comes with your installation. I will show you how to do that. That you can do. It's more powerful to do when it comes to post-processing. Okay, you can do nicer post-processing, but that doesn't mean that whatever we have done here in this section doesn't work, but that one is more powerful. So that is the other thing that I want to show you. But see that what is running, see that it's always when it's saving those files, that is slowing down things because you have this extra IO that can be time consuming. But see that this time step 0.05, see that this is the IO I'm talking to you, and see that this here, every 5 iteration is convergent. This is the ideal, not what we want. So let it run. Okay, let's see, that probably will take 10-20 minutes, I don't know. Okay, so see you later. Okay. Hi there. So in my case, the simulation is over, and see that probably took like 30-35 minutes. You might think there's a long time, but on steady simulations are like that. They're long, you need to let it run for a lot of time. In my case also it was a little bit slow because I was running also some background processes on some other stuff. And also we had a lot of input-output data. Now here we put a lot of things to save data. So as you open the folder where you were running, see that you have all these files, all this information. So this saving this, it will slow down the computation, but also this takes hard drive space. So see that you have all the files for the animation in Fluent, but also you have the Ensight files here. So see that later will be a video just to show you fast how to do this one. So here you have all the information saved for with a given saving frequency, so you can do nicer animations here, and you access all the data that you saved there. Then see that you will save in the last 5 files, okay, 5 files in Fluent. So if you want to restart from here, just open it with the case and you are done. Here you have the text file. So for instance, you open this one, you have every single iteration you will save in this information, the same for leaf and direct signals. So later we're going to do the post-processing inside Fluent, but also you can do that post-processing using external files. You have this in ASCII format, so you can open it with whatever you want, MATLAB, Python, Excel even. So at this point that you have this, you can see your here you're seeing the last, if I would recall, 1,000 iterations of your convergence monitor, but see that they go down or not. So what you are looking here is your initial residuals. You then have final residuals that always, they reach always convergence. This is the initial, and this is not a problem. This is just telling that your case is full and steady. Okay, so you see they go up. Then these are your points, the velocity that you were sampling in all the points. So see that you have all these fluctuations there, and now you can use this information now to do some other post-processing. You have your CFL number, you have CL, CD, you can change these scales now. There's no problem. You in the plots you can change it. Then you have here the facet average of Y plus in the cylinder. Here you have the mass flow, so it's oscillating a little bit straight, but see that it's a very low value. Okay, and more quantities, and these are, okay, the visualization while running, that you can see that information. So remember that all the post-processing is done in the same way. So let me go here, new, and this, you add a new plot. I want to plot unsteady statistic, and see that you can access this information. So you have the mean velocity. So all the iterations that you were running, okay, I just need to choose the plane that you were running, you are computing the statistic. Okay, so this is the average value of the whole field. Okay, so this also will slow down your computations, your computing. So you have instantaneous values and mean values, all the turbulence quantities. Then you can plot also velocity vectors. Okay, so you have it there, so that you have your nice velocity vectors there. And then as you go here in okay, here you can compute integral fluxes. So say that inlet and outlet, and should be low value, all your integral. So all your post-processing you can do in the same way that you have done so far. So in plots here, you open here and you can do the plot of whatever you want. Okay, so in this case you can plot, for instance, okay, in this case, okay, to do the plot later, I will show you how to do that. Okay, so and using this utility. Okay, and what else I wanted to show you? All the reports. Yeah, nothing else to show here. So remember, if you want to keep running this one, we stop at 80 seconds. That we impulse here max flow. Max flow time 80 seconds. Okay, max flow 10. But if you want to run, if you want to run to 100, put it here and just press calculate and we'll restart. The statistic, you will keep computing the statistic from where you were, okay? But if you want to reset a statistic, you go here, initialize, reset a statistic, okay? Pretty much that all. So in the next videos, we're going to focus in the post-processing of these fields, all the fields that we save here in the ASCII files. But also you have in memory, there is this nice tool that you can do that post-processing. And also we will compare also the same case into this, pretty much the same, but just to show you the big advantage that, as I mentioned, that I like here when running in 3D is that you go here and you pick up the wall, and for instance, you want to see the turbulent wall plus, you put it there and see that now you have this surface there instead into this line. So sometimes it's tricky to see that one, but it's not a big deal. Okay, it's up to you to choose which mesh approach you want to use to run the case. So I think this is all for this case. Nothing else to that. So in the next one we have the solution. Okay, if you don't have the solution, I will put it in the website. For instance, you don't have the final or the fast, this one, I will put it in the website up to 100 seconds, and we're going to open those to do the post-processing. Okay, that's all. Thank you for your attention. See you next time. Bye.